Right, can everyone see my screen? It should be the discussion 12 cryptography. Yep. Okay, so this will be recorded and then I'll probably post the link of Piazza later. Um, so if you see anyone in the actually no, I think I'm the only one who can see the waiting room, so I will make sure to keep checking that. Okay. All right. So unfortunately we have to have our final discussion virtually because I got COVID, but then um this is still a very important topic because it will be this is like a whole unit in for the final. So announcement, final exam review will be later at 4 p.m. at Dow 1010 with Zhongwan. I'm gonna cancel my office hour tomorrow. Unfortunately, I have to. But if people really needs it, I might do a virtual one, but I'm not sure yet. I will make an announcement if there's any changes. And then the final exam, logistics and the format are on Piazza. It will be 8 to 10 a.m. this Wednesday, and then check out Piazza for more information and for room assignment as well. Okay, so today we're gonna talk about. Oh, actually, I'm missing a few things. But we're gonna talk about cryptography chapter. The first thing that I want to talk about actually is the one-time pad, which I forgot to put it here. One-time pad. And then we're gonna talk about Diffie-Hellman. And then before we get into RSA, we're gonna talk about FLT and Euler's theorem, which will be used in RSA. And lastly, we're gonna discuss a little bit about cryptography and complexity. Try to see the connection between PMP and the cryptography unit. Okay, so for a one-time pad, which I didn't have the slide, I'm just gonna briefly go over that. It's basically using modular arithmetic, and I think Dorian went over modular arithmetic last discussion about how it's just like a clock where it let's say I'm in the class Z7, then it will just be 0, 1 to 6, right? So what one-time pad does is it's gonna make use of this property and then gonna use the idea of like shifting and then try to take the congruent in the congruent class, right? So for example, sorry, can you see my screen? I don't know why. Stop sharing. Second. Give me 1 second. Okay. So how one-time pad does is you're gonna have like first start with the encoding of each letter. So for example, A, I forgot if they use one index or zero index. Let's just use one index. Then B is 2, C is 3, and so on and so forth. So Z will be 26. So for example, let's say I choose my K1 to be 2, K2 to be 3, K3 to be 1, for example. And then my message is let's say just ABC. So what I do is I'm gonna make a shift based on the KIs, right? So for A, I'm gonna shift let's say it's ABCZ, and then K4 is 2. So A, I'm gonna shift 2, so it's gonna be so you can see of this as like 1, oh my god, 1, 2, 3, 26. So 1 plus 2 will give us 3, and then 2 plus 3 will give us 5, and then this will be 4, and then 26 plus 2 is going to be 28, but then we're going to take the mod of it, mod 26 of it, which will give us 2 in mod 26. Okay, and then we just go back to the table and find the corresponding letters. So I believe 3 would gives us C, and then 5, okay, D is 4, E is 5, so it's going to be E. And then 4 is going to give us D. and then 2 is going to give us B. Okay, so this will be how one-time pad works. And but it's very troublesome to come up with different keys for different letters. So a simplified version of it will be the Caesar cipher encryption, which they have a fixed K. Okay, so for example, let's say K equals 2, then again, let's say we have A, B, C, Z. Everything will just shift 2 behind. Okay, so this will be C, D, E, and then Z plus 2, again, will be 28. 28 is B, so forth. Okay, so we are using the same shift for every letters. Is there any questions so far? Okay, so the problem with this kind of encryption is that people can do a frequency analysis, because I think you have seen in lecture that, I mean, it's like an NLP analysis, that the distribution of the letters that we use in English, it's quite consistent. Like for example, let's say the letter E and the T is more commonly used. So if your message is very long, then people can do the frequency analysis and kind of backtrack to get your K, or even or to get each KIs. So sorry, especially when you only have one K, then it'll be really easy. People just need to like try to map it to the actual frequency and find out the K, and then can decrypt your message easily. So that's not good, and that's why we have the Diffie-Hellman and the RSA, which we're gonna discuss today. Okay, is there any questions so far? But this is like just the background to what we will be discussing. Okay, so first then, Diffie-Hellman protocol. So in this unit, you're gonna see a lot of Alice and Bob's, because they are A and B, and it makes it very easy for us to just abbreviate with A and B. So now, let's say they want to, so for Diffie-Hellman protocol, the goal is that they want to come up with a key that only 2 of them knows. Okay, and then this key can be used for, I mean, you can be used to encrypt the message using maybe a Caesar cipher or something more complicated. Okay, so the goal of it is just to come up with the key. So first of all, they're gonna decide on a prime number P and a generator G. And I hope you still remember what a generator is from last week, for the prime number P, which is basically the one that gives you like you can hit everything in the congruent class. That's the generator. So okay, we have Alice and Bob. So Alice will first choose a number in ZP star, the congruent class of P, where P is a prime number. And then Bob will also choose a number B in ZP star. And then Alice will send the generator raised to A in mod P to Bob. All right. And then Bob would send the generator raised to B, which is the number that he chose, and take mod P and send back to Alice. Then with this information, Alice and Bob can get the shared key by computing whatever that they got from the other raised to their own number. Okay, so what Alice does is she will compute, this is actually GB from Bob, and raised to A and take mod P. Okay, so this is what Alice will get. And then Bob will do the same thing. He's gonna compute, so from Alice, he got G to the A, and then he's gonna raise it to his own number and then take mod P. All right. And then because of the properties of exponent and stuff, we know that G to the BA is the same as G to the AB. And then it also holds in modular arithmetic that G to the BA mod P is the same as G to the AB mod P. And therefore, both of them will have information to the shared key that only they can compute, because these A and B are private, right? So any like anyone who only has P and G is gonna be very, very hard for them to find out the actual key because they don't have A and B, unless they want to go through the exponential, like very inefficient algorithm to find them. So that's the idea behind Diffie-Hellman, which is basically just built based on this, and then one of it has this and the other has this, and therefore they're able to get a key that only two of them could compute. Is there any question? Okay. Yeah, so it's gonna be the same. Let's look at an example, and then I have the protocol here for reference. So suppose that they agree on a prime number P equals 7 and a generator 3. And suppose that Alice picked A equals to 3. So if you look at the protocol, so we have chosen A, and then we don't know what happened on Bob's end yet. And then we have Alice, and then she's gonna compute G to the A mod P, right? So you're gonna compute G to the A mod P, and G is 3, A is 3, mod 7. Okay, and we know that this is 27 mod 7, which I believe is 6, right? So this will be the message A that Alice will send to Bob. Okay, any question? Okay, so after Alice sends this to Bob, then suppose that Bob sends back B equals 2. This is, and we know that this is G to the B mod P, right? And now we want to compute the shared key. And then because of the idea of Diffie-Hellman, which is basically G to the AB equals G to the BA, we know that Alice is just gonna raise this number to her own number, to her own A. Okay, so Alice is gonna raise this GB to the A and then tag mod P. And we know that this is 2, and we know that Alice picked 3 mod 7, so this will be 8 mod 7, and therefore the shared key is 1. Any question? Okay, so I think you probably have one homework question on Diffie-Hellman on the homework as well. Basically, what we will expect from Diffie-Hellman is probably going to be very straightforward, that we're going to give you all the numbers that you need, and then you just need to do the computation. And you might need some trick from last week, which is the fast modular exponentiation and repeated squaring and stuff to simplify your computation, because you don't have the calculators for exam, right? So that's something that maybe is a hands-on things that you should practice and get comfortable with. Okay, so is there any question on Diffie-Hellman? Okay, then let's move on to the next one, which is FLT and Euler's theorem, and this will prepares you to for RSA. Okay, so FLT says if you want to compute an exponent of a really huge number, okay, so let's say we want to raise A to the let's say n. And last week, I think Donna went over how you can do that with repeated squaring, which is first you represent n in terms of binary, and then you keep repeated squaring and then keep simplifying along the way so that the number won't get too big. But here, FLT says if you could express n in this form, okay, 1 plus k p minus 1, where k is an integer and p is a prime, then we could directly simplify this to be equivalent to A in mod P. Okay, so for example over here, let's say I want to compute 5 to the 376 185 in mod 376 183. And we know that we're given that this is a prime. So the first step that you should do is to try to break down these 376, 185 into this form, right? Or this form plus something plus, let's say, plus a b, and then so that you can write it as kp minus 1 times a to the b. Okay, so you try to get this form out first, and then given the hint that we want to use this as our p. Actually, no, we have to use this for our p because it is equivalent a in mod p. So we know that the difference between these two numbers is just 2, right? And let's just try to write this form first. So 376, 183 minus 1 will give you 376, 182. And then to make up to this number, we need to add 3 more, right? But we need a 1 here. So let's just put this 1 here as well. So 1 plus, and then we can just let our k be 1. And now we have 376, 183 back. So we need to add 2 more. And therefore, with that, then we can express our left-hand side of the equation like this. So 5 to the 376, 185 is equals to 5 to the 1 plus 1 times 376, 183 minus 1 times 5 squared. Okay, and then by FLT, we know that this is equivalent to 5. And this is times 25 in mod 376, 183. Right, because I'm just directly copying down this number. And then that is gonna be 125 in mod 376, 183. And that's the final answer. Is there any question? Okay, so basically whenever you need to compute some a to the n in mod something, if a to the n m, let's say a raised to n mod n, if n is a prime, then maybe you want to consider FLT because you have this very nice theorem that you see you can directly simplify such a big number into just a. Okay. Yeah, so that's it. Here's a remark on FLT. I think this is still how it's written in the course note, which is written slightly differently. So, but then here's the proof that they are equivalent to what I just showed you. And I mean they're the same theorem, so they're saying the same thing. So just pick whichever that you feel more comfortable using. So basically the idea is similar. If you want to use this version, is again try to express it into the form that the theorem says. And then the goal is again to simplify the modular exponentiation. And the limitation is that it only works if you're taking a mod in a prime number space, a congruent class of a prime number. Okay, is there any question on this? Okay, if not, then let's move on to a more powerful extension of FLT, which is the Euler's theorem. And Euler's theorem depends on this thing called the Euler's torsion function that express any number. Okay, so let's say it's called phi of n, and n is any integer as the okay, slightly more complicated, p minus 1, q minus 1, where p and q are distinct prime numbers. So really prime numbers are they have really nice properties that allow us to make the crypto system strong. And this is why we want to work with prime numbers. Okay, so basically, such that n is the product of the two distinct primes. So basically, just now we have the constraint that we have to take mod p where p is a prime number, but now we can work in mod n for any n. Okay, and then this n, if we could write it as a product of pq where p and q are distinct prime, then we can simplify this modular exponentiation a raised to the 1 plus k p minus 1 q minus 1, which is basically the Euler's torsion for n. Then this thing is equivalent to a in mod n. Okay, it looks very similar to the FLT, except that now we don't have to worry about whether we are taking mod prime. It works for any n. And then we just need to find p and q such that n equals to pq. And then compute the Euler's torsion function. Is there any question? And please stop me if I'm going too fast, because when it's virtual, I find it hard to control my pace because it's just me talking and not looking at anyone. Okay, so let's do this example. 5 raised to the 376 mod 35, and we know that 35 is a composite number, it's not prime, so we can't use FLT. But we could use Euler's theorem because I'm pretty nice to put a small example here where we know that 35 is 5 times 7, right? So our Euler's torsion function p minus 1, q minus 1, okay, p is 5, q is 7, they are both primes. So p minus 1, q minus 1 would be 5 minus 1, 7 minus 1, which is 6 times 4, which is 24. Okay. Okay, I think I'm gonna need more space later. So let's see. Okay, let's just keep this in mind. I'm gonna erase. Okay, so p equals 5, q equals 7, and then the Euler's torsion is 24. Okay, so now we want to express it in this form. It's very similar to what we did for FLT just now. So let's first write it out first. We want 376 to be equals to 1 plus some k, and we know that this Euler torsion is 24. And we're probably gonna have some other as well. So I think this is gonna be a very big number that we won't expect you to do by hand. Because like as you can see, this k is probably gonna be very big. So let's see. 376, 376, 376, 376 minus 2. Okay, the closest one. Okay, I'm just using calculators for 376, 376 divided by 24, and then I'm getting 1568.2.33, so on and so forth. Okay, so, and this means that it will be, our k would be 15682 times 24, and then we just need to calculate the remainder. Okay, and then if you do the arithmetic, okay, minus 15682 times 24 minus 1, and this b is going to be 7. Okay, so 376 can be written as 5 to 1 plus 15682 times 24 times 5 to the 7. And then by Euler's theorem, we know that this can be simplified to 5 times 5 to the 7 in mod 35, which is 5 to the 8 mod 35. Yeah, sorry, today we have a lot of computations and stuff. Is there any questions so far? Okay, and then now to simplify this, we're just gonna do repeated squaring because like you see 8 is a power of 2. So let me get some space. Oh my god. Okay, so now we want to compute 5. Oh, am I still sharing my screen? Okay, can see the screen, right? So now we want to compute 5 to the 8 in mod 35, right? And then remember from last week, we're just gonna compute like 5 to the 1 is 5 in mod 35. And then 5 square, you're just gonna get this 5 times 5, which is 25 in mod 35. And then 5, you're gonna compute the power of 2. So the next one you're gonna compute is 5 to the 4th, which you know that is 5 to the square times 5 to the 5 square times 5 square. And we already know that this is equivalent to 25 times 25 in mod 35, which is 25 squared is 650. And this is equivalent to okay, this is why I for my cheat sheet for my final exam, I actually have like the multiplication table on my cheat sheet for 35. So let's just do this quick math. 35 is gonna be 30. Actually, this divided by 35. Okay, so this is gonna be 30 in mod 35. Okay. And then lastly, we want to compute 5 to the 8, which we know is 5 to the 4 times 5 to the 4. And we already know that this is 30 times 30, which is 900. And then it's equivalent to 25 in mod 35. Okay. So like the nice thing with repeated squaring is that you see at this point I can just plug the 30 that I found earlier, right? I don't have to keep squaring the number until it's really, really big. Okay, and this is why I can just conclude that. Therefore, what was I trying to compute again? 5 to the, so therefore 5 to the 376 is equivalent to 25 in mod 35. Okay, any question? Sorry, I know this is a lot of math, a lot of computation, and you should try to work it on your own to get the hands-on experience and be really comfortable like doing both applying the FLT, applying Euler's theorem, and also repeated squaring for fast modular exponentiation. Okay, is there any question? If not, we're gonna talk about RSA next. Okay. So RSA, I think these are just the abbreviation of the name of a few guys who contributed to the crypto encryption system. So before we get there, let's do a quick recap on modular inverse. So we say that A inverse is the modular of or multiplicative inverse of A in mod n if the product of them are equivalent to 1 in mod n. Okay, so you could think of it as like the let's say we have x and then we take 1 over x, it will give you 1 in normal algebra. Okay, so in modular arithmetic, it's basically you have a and then times a inverse, it will give you 1 in mod n. That's the idea of multiplicative inverse. Okay? Something that make you back to 1, which is the identity. And by definition of modular arithmetic, I think Dorian have shown you like a few ways where you can write it out. That means that there is an integer k such that a inverse times a is equals to 1 plus k times n. Okay, this is just like saying if a is equivalent to b mod n, then this is the same as saying a is b plus kn. Okay, except that now a is a inverse times a, b is 1. Okay, you still have the kn. It's just another way of writing out the modular arithmetic. Okay, and then we also know that A has a modular inverse in N if and only if A and N are coprime. Or in other words, their GCD is 1. And then if P, that means that if P is prime, then every number in its congruent class will have a modular inverse in mod P, right? Because the fact that P is prime is saying that it is the only divisor is itself and 1. And that means that every number in the congruent class has an inverse because they are all coprime with P. And then lastly, we'll also talk about how we could find the modular inverse using extended Euclid algorithm, which is basically you just run the extended the normal Euclid algorithm and then get you have your x, y, and then you just update your g along the way. Sorry, x, y, and then just I think the table that we have looks like this. Oh my god. So for the forward pass, you're gonna have x, y, and then you're gonna have the quotient. I forgot how I arranged it. Q and R. You're gonna have the quotient and the remainder, and then you're gonna update along the way. The y gonna be the new x, and then the remainder gonna be the new y, and then you go along the way until you hit the base case. So you know that if you're in this case where p is prime, you know that you're gonna hit a 1. Okay, and then you can go back and find your a, b, and then update your a, b accordingly. And of course, the function should also return the GCD as well. So you have G, A, B return from the algorithm. I think I probably have fit the algorithm later. But then that's like just a quick refresher on how we can find the modular inverse. Okay, so here's just the recap. Now let's look at the protocol. And here's a reminder for Euler's theorem. So again, we have Alice and Bob, and then some information that is publicly available to everyone. So the first thing that is public is n, which is the modulus that you want to do the system in. So Alice gonna choose oh actually no. So Alice gonna find P and Q, gonna choose P and Q, which are distinct prime. Okay, so these are distinct primes. And then n would be the product of P, Q. Okay, so P is P times Q. And next, she's gonna find a pair of numbers, E and D, such that E and D are modular inverse in mod Euler's torsion of n. Okay, and another way of writing it, like just now, the way the things that I show you, you can write it as 1 plus k times p minus 1, q minus 1. All right, and now Bob wants to send a message M to Alice. Oh, by the way, so now E would be a public key, okay, and D would be a private key that only private key that only Alice knows. But she has to broadcast, she has to tell everyone E so that anyone who wants to send a message to her could encrypt the message so that only Alice could decrypt it. Okay, so E has to be publicly available for those who want to send a message. Okay, so now Bob wants to send the message, and she compute the ciphertext by raising the message to the private key E and tag mod N. Okay, so he's gonna send this to Alice. So here's where you can kind of see a very similar idea to Diffie-Hellman. Diffie-Hellman, just now we have G to the AB is equals to G to the BA, right? So now Alice, and we know that this is equivalent. So now Alice is gonna decrypt the message by raising the ciphertext to her own private key D. Okay. Okay. So she's gonna raise C to D and tag mod N. And we know by definition, C is M to the E, right? So M-E D mod N. And because we know that E times D is 1 plus K P minus 1 Q minus 1. So we can rewrite it like this. And by Euler's theorems, we know that this is equivalent to M in mod N. And thus, Alice can decrypt the message and get the original message that Bob wants to send her. Okay, any question? It's basically the same idea as a similar idea as Diffie-Hellman, where you try to leverage the properties of modular exponentiation. And now that she's using this Euler's theorem to choose like the key and stuff. To choose like this 1 plus K P minus 1 Q minus 1 so that you could like decrypt it back to the original message. Okay. And again, what you should expect in the exam for RSA is we're gonna give you the relevant numbers that you need, and then we're gonna ask you to compute some, maybe the keys, maybe the message, ask you to decrypt the message and so on and so forth. Just like what I think we also have one RSA question on the homework. It's gonna be very similar to that. So it's gonna be really straightforward, just pure computation. Okay. And let's look at one example here. So again, I have the protocol here as well for reference. So let's say, okay, so by the way, in practice, we're gonna choose a very huge prime so that it's impossible to try and error and get the prime numbers like efficiently. Okay, so but then here we're just gonna play with some toy example where the numbers are small. Yeah, and we do expect you to be able to compute it out by hand without using any calculators. In that case, of course, we will give you nice enough numbers that you don't need calculators, hopefully. Okay, so let's say Alice pick two distinct primes, 11 and 13. So based on the protocol, she's gonna compute n, okay, and broadcast this number. Okay, so n is gonna be public, and we know that 11 times 13 is 143. And then the next thing is to compute the Euler's torsion, which is the p minus 1 q minus 1, and this gives us 120. Okay, and the next thing is to pick E and D, right? The private key and the public key. So suppose that Alice pick the public key to be 17. And then to find D, she needs to find the modular inverse of E in mod 120. And that can be done by the extended Euclid algorithm. And then she obtained D equals 113. And now she'll broadcast N, which is the product of P and Q, and the private key E for anyone who wants to send a message to her. So now, let's say Bob's want to send the message N equals 5. So using the protocol, he's gonna encrypt the message by raising it to the private key, which is E, and tag mod N. So it's gonna be 5 raised to 17 mod 143, and then you should try to compute this thing modular exponentiation using either the repeated squaring or FLT or Euler's theorem. Okay, you should be able to do that and send it back to Alice. And then to decrypt the message, Alice is gonna raise this ciphertext to the private key D, and then again tag mod N, and finally get 5 as the message. Is there any question? Okay, so now let's do a quick, I believe this oh yeah, this okay, just a concept check. So suppose that you're Eve and you want to find the message, okay? So let's say Bob sends a ciphertext to Alice, okay? And then you want to try to know and try to get that message. So now, okay, suppose that you have access to one of these information. Which of them, or could be more than one of them, would allow you to decrypt the message? So I think I'm gonna open up a poll and then you can think about it and just vote here. Now you can just think about it. So for A, we have the um okay. So the first one, option A is the product of P minus one, Q minus one. And then B, you have the exact value of P and Q, which are the distinct primes. And C is a K that satisfies this equation. Okay, E times D is equals to 1 plus K P minus 1 Q plus 1. And then for reference, you have the RSA protocol right here. So I'm probably gonna open for a minute. Actually, I just realized that it should be a single, multiple answer, multiple choice, but the poll is only for single choice. Never mind. um, okay, never mind. The poll doesn't really make sense now because there are multiple answers. Okay, anyway, let's just end the poll. Apologize for inexperience in teaching over Zoom. So, okay, the answer is all of the above. Because the idea is in order to decrypt the message, you just need the private key. That's like the most important thing that you need. And I'm gonna show you how you could retrieve D using any of the information that you have there. Okay, so option A is pretty straightforward. If you have P minus one, Q minus one, then obviously you could just this is your phi n, right? And then we know that because E is publicly available, and we know the relationship between E and D, which is their modular inverse in phi n. So you could just run extended Euclid algorithm, which we know is efficient to find the private key D. And once you got D, you got the ciphertext, you could decrypt it. The option B, if you have P and Q, then you could compute the Euler torsion, and that means that you could again run extended Euclid and find D. And option C, if you have this K, then you could express P and Q in terms of K. Oh, actually, no, I'm not sure if it's still on the worksheet. But basically is that you could just do some algebra and reduce the problem to B, which is you could just get P, and you can solve for P and Q. And with P and Q, you could compute P minus 1, Q minus 1. With that number, you could run extended Euclid algorithm and get D. So if you are given any of this information, then you could get the private key D, and therefore you could decrypt the message. Okay. The last thing that we want to talk about today is RSA signature. So now, suppose that Alice is the one that wants to send a message, and she wants to prove to the receiver that this message is from her. So again, we have Alice and Bob. It's very similar. First, Alice gonna decide on P and Q, two distinct prime, compute n equals to P times Q, and then n will be publicly available. Again, she's gonna find a pair ED such that E and D are multiplicative inverse in phi n, which is in mod p minus 1 q minus 1. Again, you could express it in 1 plus k p minus 1 q minus 1. And then she's gonna broadcast the public key E. And now Alice wants to send a message M to Bob. So she's gonna compute the signature by raising the message M to the private key D, mod N. And then they're gonna send the message and the signature to Bob. And Bob can verify if this message come from her by raising the signature to the public key E. Okay, and we know that this is N the D, E. And what Bob should expect to see is that this should be equivalent to M in mod N. And we know that this works because of this, which is D times E is over here, 1 plus K times P minus 1, Q minus 1. And by Euler's theorem, we know that this is equivalent to M in mod N. And if the signature raised to the public key is equivalent to M in mod N, then Bob knows that this message comes from Alice. Is there any question? Okay, so I don't think we have time for this exercise, but then basically if for RSA signature, okay, I think you should go over this on again, the question what you should expect is very similar to this one, which is gonna give you all the numbers and you're just gonna compute the like all the numbers, and also make sure that you I would prefer if I think you should also have the algorithm, extended Euclid algorithm on your cheat sheet as well, so that you can run it to find the modular inverse, right? So first you want to find the prime factorization, find the P, Q, and then you probably need to find, given the public key E, you want to find the private key D. You need to run the extended Euclid algorithm and then get the modular inverse. And then you're gonna compute the signature and stuff. Okay. So that's what you should be expecting. Okay. So lastly, let's just wrap up the cryptography with by relating it to complexity. So basically, RSA and Diffie-Hellman, it seems like a really cool trick, right? Where you can just like compute numbers. And it looks extremely simple because all you need is just to compute the power. But then this the reason why it's I mean obviously RSA and Diffie-Hellman is not the safest cryptography system, but then the fact that they are considered as like encryption is because it is hard to solve for the discrete log conjecture. And the discrete log and also the integer factorization, these two problems are believed to be NP intermediate, which is in here. They're NP, but they're not in P. And if they're not in P means that there is no efficient decider, there's no efficient ways of solving them. And therefore, people are still believe that it's safe. Oh, sorry, it's a hard enough problem that can't be broken easily. And this is why I think when we talk about P versus NP, I say the entire cryptography is relying on the assumption that P is not equals NP, and this is why. Okay, so I think that's all for today. Thanks for a great semester, and these are the list of courses that you could try to look up to if you really like any part of the content of this class. And then I'm really happy to, even though it's just a short semester, and then I feel like it's a really meaningful semester to teach at a fast pace. And then I wish you all the best for the final. I think that's all for T76, and good luck.
Thank you.
Mhm.